Welcome back, nerds. Today, oh, good, I like it. Little smiles. Okay, you can find the arc length of something using r theta, so long as theta is given in what? Radians. Is there a way to convert between degrees and radians? So if I give you any angle in degrees and I want you to change it into radians, what is your clever choice of 1 that you multiply by to do that conversion? Pi radians divided by 180 degrees. The degrees fall out and you're in radians all of a sudden. Okay, this will become valuable. Now, arc length, if we think about it, if you have something walking in a circular fashion, the arc length is just literally the length of the path, right? Now, I'm going to walk in a large circle, and there's no real circle drawn here, and it probably is not going to be a true circle, but I'm going to walk a little circular path. And let's say that I'm going to walk along this circle, and I did this. And I'm just guessing, I probably went like 2 meters, is my guess. And it took me, I didn't really measure it, but let's say it took me 3 seconds. If you know how far I traveled and how long it's taken, there's a physical quantity that we talk about a lot early in the morning, like 8:30 to 9:30, pretty regularly. The distance I travel over some amount of time. Meters per second would be an example of that. It could be miles per hour, kilometers per day, doesn't matter what the units are. But all of those examples that I just give are a way to talk about one very important physics idea. It's velocity. Okay, so this does not happen a ton in here, but welcome to physics through the lens of Precalc for a moment. Okay, it is going to be really natural for me to go really fast because we've talked about velocity with almost everybody in here. I am not going to leave Charles behind, though, and we're just going to pretend like this is brand new for everybody while we hit it. Cool. Not any slight against you. You just don't happen to be in my first hour of physics class. So, cool. All right. Here we go. We are talking about applications. Arc length is certainly one of them. There are 2 more really big applications, and one of these is brand new to everybody, whether you're in my physics class or not. But last little section, and I'll change colors. What color is velocity in your brain?
Yellow.
I heard blue. I would use yellow, except I'm already have it. You're good. There's no right answer there, right? Okay, we're going to talk about linear and angular velocities. Now, the language is a little bit more formal here because even though we're not in a physics class, the math ideas that we're seeing, they extend past where we're currently at in physics, knowing that it's coming up in the next chapter too. Now, what does this mean? Linear, just linear. A line. Now, for this, we're going to think about this. Suppose that we have, and I'm going to draw a path of it, and gosh, the overlap is just so clear, and you're going to see it immediately. Let's say that I have a sling, and I'm like hunting. I'm an old caveman. I'm swinging above my head, like in a way that the radius doesn't change, and all of a sudden the speed is constant. The velocity, if you measured it. That is uniform circular motion. That's what we talked about, we tested about this morning. So let's just make a couple little statements here, and then we'll dig into that. First off, when you talk about velocity or speed, how do you calculate it? Velocity is just simply some distance that you travel over what? The time it takes. Everybody all right with that idea? Like, that's just the definition. Now, you might call it delta x over t for displacement, but it's the same idea here. Okay, for this, let's say that we have an object that's spinning in a circle, and it's not changing its velocity, nor is the radius of this circle changing. If I wanted to talk about the distance that it travels, would you agree that's just a part of the circle? So if it's spinning in a circular fashion, so like maybe there's a person standing here and it's like a hammer throw or something, I don't know, and here's the path that it travels. If I want to find at some point the distance that that object has moved, could it be just that distance right there? Over some amount of time, right? So through some amount of time, it moves from right here to here. Now, that is a distance, I think. Pretty sure we could measure it. In this situation, it turns out that we know how to do this. To find the velocity after we move this distance, you need to find the distance. That's it, right? Distance and time. How do you find the distance of that path? So before you answer the formula, because I see you're digging deep for it, let me just ask a different question. This distance, it has a name in our pre-calc physics unit circle stuff. Not a ray. You're on the right track. Is that what you said? A ray, remember, is a straight line. So the rays would be, if you're looking at the rays that form an angle, there is a ray that forms it, and there's a ray that forms it. But this, ooh. So not yet. We're just looking at this part here. A portion of the circumference is what I'm really looking at.
Arc.
It's an arc. Do we have a way to find the length of an arc? In radians, it's super easy, right? So check it out. If we take this circle, and I'll just say that here's the distance that we travel, I'm not going to call it the distance though. In this situation, the velocity v would be equal to the arc length divided by time. Now, it's the same thing, but instead of saying, oh, it's some distance, we're literally saying it's the length that you've walked, that you would travel along that arc. Everybody's so cool. All right, now we're going to make this big statement because degrees are fine and dandy and probably more comfortable, but what's way cooler than measuring angles with degrees? Radians is the appropriate answer. So check it out. If you have your picture, I'm going to put an angle theta right there. This is an angle whose vertex is at the center. What's the language that we use? Something angle. Close. I bet I can find it over here. The angle that gets formed at the center of a circle. We said it somewhere, I'm sure of it. Oh. Maybe I didn't write it. Did we use the language central angle yesterday? I feel like we did, but I could be wrong. I thought it, if nothing else. Okay, we're going to call this a central angle because it's at the center of the circle. All right, if this central angle theta just happens to be in radians, or we make it that way, if theta is in radians, we get, and we're just going to rework this equation here. V is equal to, well, how do you find arc length? Directly above in your notes, and this is why radians are so nice. Louder, because you're correct. R theta over time. This is just some distance along the arc given by r theta divided by time. Okay, now when we think about this velocity, because we're going to see another one here in a second, if we were to, like if this is connected to a string and we're swinging it, and I cut the string, what direction does it go? The object. Does it keep turning even though I'm not holding the string anymore? It goes tangent to the circle, is what you were saying. Sorry to interrupt. My bad, I do that a lot. Okay, but I don't, like, it leaves tangent, I'm fine with that. Does it do this once it leaves? So it leaves tangent to the circle in a line. Everybody good with that?
I said that, but I don't really understand what that is.
A tangent touches at one point and only one point, and it glances by. Okay. Yep. So this is a tangent, and when you see this in calculus, and you don't have to draw this, but
I know that like cosine and sine and tangent all have their own lines.
So this is very different, just so you know. The tangent that we use here is related, but could you draw a line, a straight line that touches just that point on this little area?
No.
Like,
it would touch.
so that touches, but that's not tangent, right? It doesn't glance by. What we'll wind up doing in calculus, inevitably when you get there, is that's my tangent. It touches exactly once in a circle and it glances by.
Like it follows the same, it follows the path?
Yep.
Okay.
Cool. So here we have this whole idea that we've just discussed. This is known as linear velocity. It's how fast the thing would travel if it weren't being turned by, not our focus, but what causes this thing to turn into a circle? What sort of force? Centripetal. Cool. This is linear velocity. Okay. In contrast with this, we're going to get a new Greek letter out of this. This is all linear velocity. Now, if I just said how fast is it moving, that's literally like if you were to cut the line and it flew straight, or if it didn't, you can think about there's velocity, like obviously you're moving quickly as you go around a circle, but that's linear velocity. We have a different type of velocity that we look at. So I'm going to draw in white here, and let's just say we have a clock. Okay, and we were to watch this clock go for however long. Clocks have hands, I think, right? Okay, what's the longest hand on a clock? A second hand, okay. So check it out. Let's say that we have this clock here, and it's huge. I don't care how big it is. If I said this second hand takes 1 minute to go all the way around, and it's gonna drive me crazy, but it does that in 1 minute. Everybody cool with that? Okay. Depending on the size, this could be going really, really fast, because if I imagine I have like a 50-foot pole, and I just do this, do you agree the end of that pole is just screaming through the air? Because it travels a huge distance as we get really far away, right? Okay, if I compared this to another clock that you might find on your wrist, a wrist clock we'll call it, that seems natural. And here's the hand that they go for 1 minute. If there were an ant or a person, I don't care what it is, living at the end of this one and at the end of this one, who's going faster in your opinion? The little one? The bigger one. Now, I agree with you in a linear sense. Okay, it would go way faster, right? The further away you are from that moving arm, the faster it's going to move. However, that's only one way to talk about speed. When we talk about speed and rotating stuff, there's another viewpoint. I'm going to make the claim that that big clock that we have on the board travels 2 pi radians every minute. That second hand, every minute it makes a full circle, right? 2 pi radians per minute. Are you guys okay with that? Or if you'd rather, in the terrible, gross way to do it, 360 degrees every minute. Okay, the clock on the bottom that we just agreed that the piece goes way slower at. If I said it's way slower, but it also spins at 2 pi radians every minute. When we think of it that way, we would argue that they have the same speed, right? So it's just really what's changing. Is it your physical position that's changing or the amount of rotation? And they're different ideas. So we get to talk about that new different idea. And in my mind, this feels orange peachish colored. Nope, bright orange. So here we go. We get this lovely idea with linear velocity, but we're also going to give ourselves a new definition, just real quick, where we're going to discuss angular velocity. Okay, in linear velocities, the question is, how much distance do you travel through over some amount of time? Okay, fine and dandy. Instead of distance being what's changing with an angular velocity, what do you think is going to change? Louder? The angle is what's changing. So it turns out that this is exactly it, and we get a new Greek letter. Okay, angular velocity, we are going to use omega is the letter that we're going to use. It looks like a fancy W or a terrible W. I actually kind of hate it. But here's omega. It's a lowercase omega. The uppercase is this, and it's much cooler. Different meaning in physics and stuff, but omega, and this is your angular velocity. Well, well, well. Come back. Cool. Angular velocity, that's it. Now, when we talk about this, it's the same idea that we just saw. If you know how far you've spun over some amount of time, and we all just agree that we're going to measure from the center of the circle to make sure we're all doing the same thing, you only have to look at delta, or we don't even need delta. We'll just say it's a central angle over time. Okay. Now, in this sense, all that we need is theta. That's our central angle. That's how we'll define it over time. Notice, not a single time here have I told you if it has to be in degrees or radians. Doesn't matter for this one. Which one are we going to use? Huh? Say it again. Correct. It's radians. Unless specified, everything in here is radians. So, we're going to do a problem with a little bit of all this. And let's just jump in. I'm going to use a little editing magic. JV, how's the flight? A little shaky? The whole way or just the landing? Good. I mean, not good that it was shaky, but all right. So, little editing magic here. Put this up here. What's RPM? Rotations or revolutions per minute. Where's RPM common? Vehicles. You see it, and if you look next time you're driving, my car doesn't have it, so maybe they don't all have it anymore. It's weird. RPM is revolutions per minute, and on your car it says times 1,000. So cars move fast. This one does not, apparently. Okay, I have 2 questions I want us to find. What is... Whoa.
Well, you can't. The wind turbine can't rotate at 1,000 RPM.
I mean, it could. It'd just probably explode.
Right.
What is the angular speed? And we're going to say in radians. Radians per minute, I suppose. Okay, and then once we knock that out, you can save space until you get there, but if we asked about the angular speed, what else might we be asking about? 2 versions of velocity. There's angular velocity and linear. So how fast in the linear sense, and I'm just going to write linear here, does the tip of each blade move? Cool. All right. Here we go. Angular speed. Well, how do we even jump in? Here's what I'm going to suggest. I want you guys to play around with this for about 2 minutes. Then I'm going to make you guys trudge me through it. Cool. Try it out. We have all the definitions, hopefully, on your page. You're looking for the angular speed first, and I want to know how do we do it. A couple minutes, and then we'll come back together. Well, I'm out of ideas. I just didn't even have a single idea. I refused to try it because being wrong is just shame. No. But what do we do? We're looking for the angular speed. Well, let's think about it. We have how many RPMs? So I'm not going to really do them all, but I want you guys to help me count in radians, okay? I'm going to spin in radians, and it's just going to be I'm a windmill at this point in time. Okay, so here we go. I'm going right now to here. How many radians have I done? Not 2. 2 pi. That pi is super important. Okay, how many total? 4 now, right? So I'm not really going to do it, but imagine I did this 12 times. How many radians has that blade traveled? 12 full circles, each of them are 2 pi. So my theta that we're looking at, and I'll just write it out, here's change in color. I know that omega, which we use for angular velocity, is the theta that we move through over the time. So in 1 minute, I'll put that in the denominator, 1 minute. And how many total radians would that fan blade move through? 24 what? 24 pi. Okay, check it out. We have it. This is it. My angular velocity is 24 pi radians per minute. That is the answer. Now, could you change this around if you wanted to? Could we make it per second and divide everything by 60 if we really wanted? I could have it per second if we'd rather. Do you want to? Cool, me neither. All right, super hard. Super easy, I think I can argue. Okay, this one's a little bit harder of a, it's not really any harder, it's more computationally heavy. You guys have already told me how many full circles there are, right? Okay, and we're trying to find the distance traveled. So, gosh, 24 full circles is like 24 circumferences, yeah? How on earth could we find 24 circumferences? I want you to find me the actual distance that this object travels, either in 1 revolution or in 12 revolutions per minute. Let's do 12. Find me the distance that an ant would actually move through space over the course of 1 minute there. Talk it out. We'll come back and pull it together. If you can get to this point, which is, I think, how we defined it a moment ago, right? S equals R theta is how we're looking at it. That only accounts for the distance you travel as long as you're really careful with the radians, right? Now, 12 full circles is what we've made in that minute. How many radians did we say that was a second ago? 24 pi of them, right? Because it's 12 times 2 pi each. Okay, so let's just keep working through. What's the radius? 112 what? Feet. And I'm going to do what I do in physics. I'm going to include the units above so they're easier and don't confuse me as we go through. How many radians? 24 pi is how many radians we've gone through. What's a unit on a radian? Nothing. So when I multiply 112 feet by 24 pi radians, it's just that number of feet. Cool? Over, how much time did we go to make 24 pi radians? 1 minute. Now, as you look at it, if you just see the units that are left, we have feet per minute. Is that a way to talk about velocity? I think so. I have no idea what 112 times 24 pi is off the top of my head, but you guys are going to hook it up. It's big. 4222? 4222.3. I think you might have forgot pi. You did put pi. Did you do 24? That'll do it. Way bigger. That didn't seem big enough. 8444? 0.6. Can I somebody second that? I don't know where I put my calculator. Okay, that's feet, right? Per minute. Is that fast? So 8,000 feet per minute, 8,500 feet. I'm just estimating here roughly. A mile is how many feet? 5,280, that's right. Thanks, Felicia. Okay, as we look at that, this is like a mile and a half. A mile and a half per minute. Okay, that's 90 miles per hour. That's pretty quick. It's not crazy fast, but it's pretty quick. It's not exactly 90, but that's just my estimate. Okay, hard. As long as you're careful with the theta that you use and you keep that in mind as you're working these problems, they're pieces of cake. All right, we have one more little piece to look at, and I thought I was going to have like half an hour. We'll have like 10 minutes for homework, but it's not going to be a super long homework, so cool. Okay, think back. We're back in geometry land for a second, and I guess before doing that, any issues here? Does this stuff feel okay to everybody? And if it doesn't, that's a terrible way to ask that because you don't want to be the one person that says, no, this doesn't feel okay. If there's issues with it, when can you talk to me? As like now, first of all, would be a good time. After class, at lunch, after school, before school. You can hit me up on X, but I probably won't reply because I get like a lot of DMs every day. That's a joke. I don't have that. That's the right terminology, though, I think. Okay. What's a sector of a circle? An arc is a part of the circumference. How about a sector? Part of the area. So it's like a slice of pizza. One slice of pizza is a sector of the circle. So one more awesome application of these. And if anybody's dying for the proof, we can do it tomorrow. But we're just going to talk and define it for ourselves here real quick. The area of a sector. And I'm going to sketch. I wonder if I had a circle last. Nope. Don't know what I pasted. Not a clue. Here's a lovely circle. And I'm going to just draw it nice in standard position as normal. Here is an angle theta. And we'll see. There's a sector. Hey, it did not do everything, and I don't know why sometimes it does. There's a sector of a circle. And I'm going to make it a black writing so it's a little bit easier to see. Cool. All right. So if you want to define this area, and we'll think for now at least, we'll think in degrees. That is theta out of how many degrees? 360 degrees, right? So you could do theta over 360, and that's going to give you a percentage of the circle. And then you just need to know what percentage of the area that is, right? How would you find the area? You would do pi r squared. Now, as we look at these things, some awesome pieces shoot out. If we're in degrees, and you can do every problem this way, I'm going to comment on it relentlessly just so you know. But if you're in degrees, the area of this sector area would just be theta out of how many total degrees? So theta degrees of 360 degrees times pi r squared. And this is a way that is presented when you learn this in geometry and you start talking about it. Or if you didn't learn it, my hope is that logically you agree with this statement. Even if you did learn it, I still hope you agree with it. Okay, in contrast with this, it is so nice in radians. If we have an angle theta that's in radians instead, this gets much simpler. There's no 360 part needed, not even a little bit. Now, again, the proof we can knock out tomorrow if you'd like to, but it turns out it is exactly 1/2 of r squared theta. Does one of those look like an easier calculation? Okay, follow up. Why don't I have a pi anymore? It's going to be in my radians. It's going to be hiding within it because pi is a part of the definition of radians. Cool. I want to do one problem together with this. And let's check it out. And we don't have a ton of space. So here we go. Example. I want the area of sector. And I'm going to be way less wordy than your book will, okay? If, and I'm just going to give you two things. The radius of the circle, I don't know, let's say is 5 meters. And that angle theta that we're trying to find the area that forms that sector is, I don't know, 30 degrees. Okay. Could we solve it with the information that's given here without doing anything else crazy? Is that how we're going to do it though? We're going to make one quick step to make the calculations easier overall. Something about it that I hate already. I don't really hate it, but for this chapter, I hate it. Gosh dang, degrees. Well, if I have 30 degrees and it's in degrees, which it is, I want to convert it to radians, but you know, I just don't remember stuff. What number can I multiply by that doesn't change anything? 1. And I know if I want degrees to fall out, they better be down here. All I need is any conversion between radians and degrees. There's a nice one we use. Pi is half a circle in radians. So here's a half a circle of rotation over 180 degrees of rotation. Okay. Yesterday, when or the day before, I don't remember, we multiplied through and said 30 pi over 180. I always simplify first, just so you know when you're looking at my math. 30 over 180 is 1/6. Times pi is pi 6. So I'm just going to say, check it out. Theta is pi 6. This is the amount of rotation that we make. Notice the pi is now automatically back inside of our calculation from pi r squared. Question? Because when we're in radians, what's the unit on a radian? There isn't one. We can say radians. That's a great question. Why do we take out degree? Because they don't feel like a unit. But if I did this, Kalisha, and you don't write it, if I put feet, and then I cancel them, are you comfortable with that? What's foot divided by foot? Is it? What's 5 divided by 5? What's anything divided by itself? So a foot divided by foot is, how about a degree divided by degree? Boom. Yep, they're just one out. Okay, once we have this, we're almost done, right off the bat. How on earth do we find the area? One half of what? And what is r in this case? So 1/2 of 5 squared times theta is pi 6. And I'm going to keep exact answers as frequently as possible. That's half of 25. Or 25/12 if you'd rather. I like 25/12. 25/12, and I'm going to write this awkwardly for a second. Why over 12? Yeah, this is 1/2 times 25 over 1 times pi over 6. All the denominators become 12. Only thing left in my numerator? Pi. And what was our unit again? The radius was measured in meters, and we squared it, so it better be square meters, which is how we talk about area. I'm convinced this is worked out. We're done.
What is that? Is that a Greek letter that you're using? That like weird. Is that just a 6?
Where?
I just cannot tell what.
This?
Yeah.
That's a goofy 6, yeah.
Okay.
Yep. Mrs. Holloway's 6s look like this, and I hate them.
I thought it was like a not finished B.
It is.
And on the next time,
Nope, that makes sense. It's a 6. That's my bad.
No. That's.
Not very often I feel like I have to explain my handwriting. Sometimes. Cool. Well, that's all I got. Riley, do you still have my notes? Did I take them?
We still have.
Will you tell me homework 4.1.2 on the very bottom of the right side?
Page 270, 35 to 38,
Okay.
51 to 53, 63 and 70.
Cool. Okay, 70 is one of my favorite problems. It's legitimately my favorite problem from 4.1. I love that. With that in mind, I don't love that it's so easy that we don't even have to think about it. That's not what I love about it. I love the complexity and the simplicity that we get from the complexity when we understand this. With that said, my advice for you would be start on 70 because you'll probably have questions. But if everybody starts on 70, we'll probably be able to pull together and make sure that everybody's able to answer it by tomorrow. Cool. All right. I'm going to give you guys 10 minutes to work. Baller. The wipers on the bus go... No, the wheels go round. Wipers don't go round. That'd be weird. Swish, swish, swish. Left and right. Back and forth, whatever you want to pick. Okay. So, I'm going to help you with this. This problem, one of the parts I like about it is it requires that you draw it and make sense of it. I'm going to do it on a different classes thing so that I have space for it. Okay. Everybody agree that back windows are kind of shaped like this. Or front windows. I don't really care what they're shaped like. Okay, let's imagine you're driving a box. This is what it's going to be shaped like, right? Okay. With, hypothetically, you have like a super muddy window, and it's like this. You can't see through it. That's a bummer. When you move your wipers back and forth, they're connected to wiper blades, first of all. But when I actually go through it, is this what's going to happen after my wiper blade runs? Is it going to do that? No. What's the shape going to look like when it's cleaned? It's going to look, or at least a portion of the circle, whether it's half or not, depends on your wipers. But I do think that it's going to do something like this. And it might even clear up all of it. But has anybody's ever come down to here all the way? That is not what they look like. Because when you look at wiper blades, it's such a cool, specific conversation. When you look at them, there is an arm that they're connected to, a central pivot point here. And then the blade itself doesn't go all the way down, does it? So the blade itself only covers like, I don't know, this much of the wiper blade's arm. And then what inevitably winds up happening then is that circular path is the path that gets formed and gets cleaned. Okay. On your problem, like, did I lose you? Okay. On your problem, they give you some lengths. And this is where it can be misleading. You do not have to draw wipers like this on your screen, your paper. This is what I would draw. Here's an angle, and this is the same thing. I have an angle theta. I don't remember what that angle is, but I think you're told what it is. 125? Okay. Beyond this is number 70 what? 70. Okay. All right. What's the total length of this segment? That is 25 inches. Okay, if I read a little tiny bit more. However, it wipes the windshield over a distance of what? Which means not to scale, but that is just saying that, hey, this is the real only part that contacts the window, right? And this is 14 inches. You are asked to find, I believe, the area covered by the wiper. And I think that this is as big of a push as I want to give you. There's a couple different circles that could be formed up here, though. There's a non-clean area, like all, I'm not going to go any further. That's enough, I think. Cool. Do it to it. Baller.